Welcome to this lecture number 37 on this NPTEL course on fluid mechanics for undergraduate chemical engineering students. The topic we are currently discussing is flow through packed beds. So, we will complete the discussion on that topic, flow through packed beds. We started this discussion in the last lecture, lecture number 36. So, let me briefly recap what we are doing. So, a packed bed is essentially a container with lot of particles or packings of different shapes. For simplicity, let me draw particles of spherical shape in this picture, in this cartoon essentially. So, you have a distributor through which fluid is made to flow, let us say a gas is made to flow. And the idea of having a packed bed is that the effective surface area per unit volume for contact between, let us say, the gas and the solid surface, or the gas and maybe there is a absorption going on, gas liquid absorption going on. So, the surface area per unit volume increases if you have packings, because the interfacial contact area increases dramatically the moment you put in packing. But here we are not concerned with the mass transfer aspects of the problem, we are rather interested in the fluid mechanics aspect, which namely what is the pressure drop that is required to make a fluid flow in such a packed bed. So, the model we had, well, before I go to the model, let me also make a general comment that this flow process is extremely complex, because in principle if you want to solve it, you have to solve for the Navier-Stokes equations with no slip boundary conditions in innumerable number of particles, and each particle is arranged in a very random way. So, it is very difficult to solve the problem exactly, it is almost impossible. One requires extraordinary computational resources and sophisticated algorithms to solve for the flow through such a bed of particles, but we will come up with a very simple model which will get the right trend for the pressure drop except for a dimensionless constant. So, the model is the following. If you look at flow through a packed bed, there are channels through which fluid is flowing. There are empty passages in the packed bed through which fluid is flowing. For example, I am drawing some passages like this. So, essentially the model we are going to have is that a bed of particles can be considered as a collection of bundle of tubes. So, although the cross section of the tubes are extremely complex, because the path of this fluid into this bed is extremely complex, but to simplify this further, we are going to assume this to be a bundle of straight circular tubes. That is the model we are going to have for flow through a packed bed. But the key thing that we are going to match is that from the reality to the model is that the effective surface area, the surface area per unit volume is the same in model and reality. Model is this, the bundle of tubes, and reality, and the porosity or the void volume is the same in the model and reality. With these guiding principles, let us move ahead. So, let us assume that first let us equate the surface area. So, let n be the number of such tubes, let pi dq d equivalent time L, pi d equivalent times L is the surface area of a single tube. If you have a tube of some equivalent diameter, and L is the length of the tube. Here we are assuming that the length of this tortuous paths is the same as the length of the bed, although if you can draw, if you really measure the length along the contour of the tortuous path, the actual length will be greater than L, but for simplicity we are going to assume that it is same as L, and we are going to correct all this with experimentally fitted parameter at the end. But right now let us move along with this assumption. So, this must be equal to the actual surface area that is present in the in the bed of particles. Let S naught be the cross sectional area of the. So, if you have a bed of particles, this is the cross section area of the bed, empty bed, L is the length of the bed, 1 minus epsilon is the epsilon is the void volume fraction or porosity, 1 minus epsilon will be the solids fraction times. So, this is the total volume occupied by particles times the area of a surface area per unit volume of a single particle, and for a sphere that is 6 by dp. For a non spherical particle we corrected that with what is called a sphericity. It is this connotes or it signifies the deviation from a spherical particle. Okay. In general it will have phi s is greater than 1. Okay. The sphere has a maximum volume per maximum area per unit volume, sorry, minimum area per unit volume. So, this will be actually sphericity will tell you the deviation from a spherical particle. So, this will be less than 1 for non spherical particles, okay, because any non spherical particle will have more surface area for the same volume. Okay. Now, having done this, we also require the second relation. This is the first relation. The second relation is that the void volume in the bed, which is S naught L epsilon, is the same as the total volume of the n channels. See, that is the amount of volume that is available for flow. Okay. So, the volume of n channels is pi d equivalent squared 1/4, that is a cross sectional area times the length times n is the number of the such tubes. Okay. So, by equating this, by using these two, we can get an expression for D equivalent. So, D equivalent is 2/3 phi s dp epsilon by 1 minus epsilon. Okay. That is the equivalent diameter of a tube through which fluid is flowing, and the model is that there are n such tubes in a bed of particles, n such tubes that model a bed of particles of porosity epsilon and particle diameter dp and sphericity phi s. Okay. Now, the next thing is what is the pressure drop. The pressure drop will depend on the velocity in the tubes. The velocity inside the bed will be different from, suppose you have a bed, okay, and if the bed is empty, if S naught is the surface area and Q is the volumetric flow rate, Q by S naught is called the superficial velocity. Okay. If there were no particles, this would be the average velocity of fluid present inside this container, but we do not have all the space or area available for flow, because only a fraction of it is available for flow. So, you would expect that the actual velocity in the interstitial gaps will be greater than V naught. So, that velocity is nothing but V naught by epsilon. Okay. If epsilon is a porosity, okay, then the actual velocity will be greater than the superficial velocity, because only that much area is available to for the fluid to flow. We can derive this in a very simple way. Q is nothing but V naught superficial velocity times S naught, that is also equal to n pi d equivalent squared by 4 times the actual velocity in these tubes. So, we can relate these two to get what is V in terms of V naught. This is 4 V naught S naught, okay, divided by n pi d equivalent squared. Okay. But we also know what is n pi d equivalent squared by 4 from this expression, from here, from this expression. So, we are going to use that. So, n pi d equivalent squared by 4 is epsilon naught epsilon times epsilon. So, I will get V is V naught by epsilon as I claimed. Okay. So, the actual velocity is the superficial velocity divided by the porosity. Okay. So, now we have an idea as to what is, we know what is D equivalent, we know what is the velocity. So, we can know what is the relation between the pressure drop and velocity if we know what is the flow regime in these tubes. So, there are of course two flow regimes. The flow regime could be laminar or turbulent. So, we could take both the limiting cases. So, let us assume that the flow is at low RE. So, the flow is laminar. Okay. So, we can assume that the delta P by L will be given by the Hagen-Poiseuille velocity relation for laminar flow in a tube. So, this is the Hagen-Poiseuille relation for pressure drop versus velocity, average velocity. Now, we are going to instead of d we are going to use dE, D equivalent, and then we are all set to derive the pressure drop relation. So, delta P by L is 32, and instead of V we are going to write V naught by epsilon times mu times 1 by D equivalent squared. Okay. So, delta P by L is nothing but 32 V naught by epsilon mu times 1 over 4 by 9 phi s squared dP squared epsilon squared times 1 minus epsilon whole squared. So, delta P by L is, if I do the simplification, 72 V naught mu by phi s squared dP squared 1 minus epsilon squared by epsilon cube. Okay. So, this is what we have. Now, this expression for pressure drop, okay, divided by length, okay, it has a prefactor of 72. Okay. Now, experiments tell us that because of the various assumptions we have made while deriving this expression, the real problem is extremely complex. There are tortuous paths through which fluid is flowing, but in reality in this model we have assumed the channels to be of simple cross section, circular cross section, and I mentioned that the actual length of the flow path of any fluid particle is not exactly the bed height, which is L, but it could be more than L. Typically it is twice L. So, this factor 72 is not really correct. Okay. So, this in fact if you think approximately that the bed should be of 2 L. So, if you take this the actual length of the tube is 2 L. If you take this here, you would expect something to be around 140 or 144, and in reality that is what happens. If you do experiments, okay, you will find that this becomes, so experiments tell us that at low Reynolds numbers, okay, delta P by L is 150 V naught V bar naught mu by phi s squared dP squared 1 minus epsilon squared by epsilon cube. So, the 72 is modified to 150, but what is very interesting and what is very instructive to understand is that even a simple model is able to predict the functional relationship between delta P by L and various other variables such as the superficial velocity, viscosity, porosity, diameter of the particles and so on in a very exact way. The only thing that is different between the simple model and experiments is the prefactor, which instead of being 72 it turns out to be 150, and that is physically because of the fact that the length of these tubes through which, so to speak, the tubes over which or the passages over which the fluid is flowing is not quite the length of the bed, it is more than the length of the bed. That is the reason why you find this prefactor to be different. Okay. This equation in the literature is called, in textbooks is called the Kozeny-Kármán equation. Okay. So, this is valid for smaller Reynolds numbers. If Reynolds number is defined based on the particle diameter and the superficial velocity and the fluid properties is less than 1, then you would find that this this correlation works very well. Okay. And there is one small difference, you also include 1 minus epsilon. This is the way Reynolds number based on the particle is defined. Okay. Now, so for a given system, this appears like you can rewrite this expression as V naught being proportional to delta P by mu, sorry, delta P by L times 1 over mu. Okay. So, this is called Darcy's law for a porous medium, for flow in porous medium, that the velocity through which fluid is flowing in a porous media is directly proportional to delta P by L and is inversely proportional to the velocity, viscosity. So, this is often used in understanding fluid flow through porous materials like sand and other groundwater transport and so on. So, whenever you have flow of water in under the ground, okay, it is almost like flow through a porous bed of mud and sand. Okay. So, this model represents, this model is useful to describe such flows, porous media flows. And now, the point is, we do not have just flow at low Reynolds numbers, we could have flow at higher Reynolds numbers also. So, for high Reynolds numbers, okay, we cannot use the laminar flow relation for flow in a tube. So, remember the delta P by L is 2 F rho V squared by D equivalent. This is the friction factor for flow in a tube. We know that delta P by L is related to friction factor through a definition, and the definition is this is the tube friction factor, which we already know from our discussion on flow through tubes. Now, we can now therefore write delta P by L is 2 F. Now, we will put a constant lambda 2, and then we will fit the constant based on experiments. Instead of V, I am going to write V squared, I am going to write V naught squared by epsilon squared, and instead of D equivalent, I am going to write 1 minus epsilon. So, this is something that we are already derived for the equivalent diameter. The equivalent diameter is nothing but 2 by 3 phi s dp epsilon divided by 1 minus epsilon. So, that is all I am trying to write here. Okay. So, after simplifying, delta P by L is nothing but, I will cancel this 2 with this 2, okay, 3 F lambda 2 rho V naught squared by phi s dp 1 minus epsilon by epsilon cube. This is at higher Reynolds. I mean, this is at, I am not saying whether it is higher Reynolds number or anything, but I am writing the delta PBL in terms of friction factor. Now, I am going to argue that at high Reynolds numbers, at very high Reynolds numbers of the order of 5000 or something. Okay. Now, the flow is turbulent, and that the tubes, I mean, if you look at the real bed, the tubes, so to speak, are very rough through which the fluid is flowing, and when the tubes are very rough, the friction factor for flow in a rough tube becomes independent of Reynolds number in a turbulent flow. So, the friction factor becomes a constant, it is approximately a constant independent of Reynolds number Re. So, I am going to use that input from flow through rough tubes, okay, and we will get delta P by 2, sorry, delta P by L turns out is 1.75 divided by phi s dp rho V naught squared 1 minus epsilon by epsilon cube. This is after correlating the data, correlating this expression with experimental data, people find that this 3 times f becomes roughly 3 lambda 2 times f becomes roughly 1.75. Okay. So, that is the experimental data that tells us that the combination of these numerical constants 3 lambda 2 and f naught is a constant independent of Reynolds number now, because we are in the highly turbulent regime in a rough tube. Okay. So, we get this. Now, this is called the Burke-Plummer equation, Burke-Plummer equation for high Reynolds number. We are essentially saying that in this bundle of tube models at high Reynolds numbers, if the tube is very rough, if the tubes are very rough through which the fluid is flowing, which is the case in porous media, in packed beds, then we can actually treat the friction factor to be a constant independent of Reynolds number and correlate this experimental data, correlate this expression with experimental data and fix the constant to be whatever that agrees with experimental data, turns out to be 1.75. Now, there is another approach which linearly combines, which merely adds these two expressions, the Kozeny-Karman equation and the Burke-Plummer equation, and it claims that it is valid for any Reynolds number. That is called the Ergon equation. The Ergon equation is merely an addition of just a superposition of the two results, 150 V naught mu by phi s squared dp squared plus 1.75 divided by phi s rho V naught squared by dP 1 minus epsilon divided by epsilon cube. Okay. So, this is the Ergon equation, which is merely an addition of the two results that we have obtained so far. Okay. So, people often define rho by G naught as 1 over V naught, or G naught squared is rho squared V naught squared. Okay. So, rho by G naught squared therefore becomes 1 over rho V naught squared. So, whenever you have 1 over rho V naught squared, we convert it to rho by G naught squared. So, delta P rho by G naught squared dP by L, this is a non-dimensional epsilon cube by 1 minus epsilon. Okay. This is a non-dimensional pressure drop, it is essentially like a friction factor, okay, is 150 times 1 minus epsilon divided by phi s squared, okay, times dP G naught by mu plus 1.75 divided by phi s. Okay. Now, if you define the Reynolds number based on particle as rho V naught dP divided by mu 1 minus epsilon, this becomes dP G naught by mu 1 minus epsilon. So, this is essentially 1 over REP. Okay. So, you can rewrite this expression if you define the friction factor of the bed as this is the friction factor of the packed bed, then F bed becomes simply 150 times 1 minus epsilon. Okay, sorry, we can rewrite in terms of the Reynolds number which we just defined, 150 divided by phi s squared, Reynolds number based on the particle, plus 1.75 divided by phi s. This is the non-dimensional Ergon equation. Okay. So, what this equation is telling you is when REP is less than 1, the first term dominates. Okay. When REP is larger than 1, this dominates. So, and when REP is comparable to 1, it is neither small nor large compared to 1, then you would have the combination of the two work very well. Okay. So, if you plot the experimental data, in F bed log F bed versus log Reynolds number based on particle, okay, you have the reality to be like this. Okay. So, at low Reynolds numbers you have the Korsnick-Harman equation, at higher Reynolds numbers you have the Burke-Plummer equation, and at intermediate Reynolds number you have the Ergon equation. Okay. So, this is how one predicts pressure drop in flow through packed beds. So, these equations are very useful in the design of unit operations such as absorption towers involving packings, and all that we need is what is the sphericity of the particle and what is the porosity of the bed, which are easily determined experimentally. Once you have that information, then we are ready to design the bed, that is at least the fluid mechanics aspects of the bed, what is the pressure drop requirement, what must be the pumping requirement, how to design pumps for running a packed bed. You need to know first of all what is the flow rate that is desired and what is the pressure drop that you require. So, that pressure drop can be calculated using this bed friction factor, and once we have this data we can design a suitable pump for such unit operations. Okay. Now, the next topic that we are going to discuss is related, to packed bed, but it is slightly also different. It is called fluidization. Okay. Now, in many chemical engineering operations, you want to increase the contact area between let us say if these solid particles or catalyst particles on which reaction is happening, you want to increase the surface area, and at the same time you also want to ensure good mixing between various parts of the reactor. Okay. So, what is normally done is that you have a bed of particles initially. For simplicity, I will draw a spherical shaped particles, and let us say you pass a gas. Okay. So, initially it is a packed bed, but when what is happening is initially the weight of the particles acts downwards, the gravity is acting downwards, okay, is now balanced by the pressure drop. Okay. The pressure drop that you exert to make the fluid flow is essentially balanced by the weight of the particle. Okay. If you do a macroscopic momentum balance, that is what will show up. Okay. If you take this entire thing as control volume, okay, if you neglect wall friction, the main dominating forces are essentially the pressure drop that you apply and the body force that acts on the entire bed, which is essentially due to the weight of the particles that are present in the bed. Now, initially when the drag force around each particle is such that they are not able to lift the entire bed, then the pressure drop will go on to just balance the weight of the bed. But as the velocity is increased further and further, there will come a point when the drag force on these particles that is present in the bed will overcome the weight on the bed, that is the pressure drop will be able to overcome the weight of the bed, and the bed will start expanding. The moment the bed starts expanding, the particles will no longer be static or in contact with each other, they will start moving almost like a fluid. So, such a state of a bed wherein the particles are no longer in contact with each other, but they start to move about more easily almost like a fluid, is called a fluidized state of the bed, or it is just a fluidized bed. Okay. And the onset of this process is called fluidization of the packed bed. Okay. So, this is the idea. So, we want to, in many chemical engineering operations, for example, in petroleum refining, you have this fluidized catalyst crackers, FCC units, which tend to process, which are used in processing crude oil to convert it to various hydrocarbons. Okay. So, we are of course in this course we are interested only in the fluid mechanics aspects of the problem. The question we want to ask is, based on whatever we have studied, whatever we have understood so far in packed beds, can we predict what is the velocity that is required to fluidize a given packed bed? Because if you want to design a fluidized bed, you want to know what is the flow rate at which you must send the gas, so that the bed remains in a fluidized state. Okay. Other design requirements are such that the fluidization should not be such that the particles go out of the bed. Okay. There should not be entrainment of particles outside the bed, because the gas will come in and go out. Okay. But when the gas is going out of the bed, it should not take away particles with the bed. So, we have to worry about those issues as well. So, we will try to address all these issues based on whatever we have done so far. Okay. Now, the idea is very simple. You have a fluidized bed. Let us imagine that the length of the bed initially, you have a packed bed, length of the bed is L and the pressure drop is delta P over a length L, and you are initially sending gas with velocity V infinity, the superficial velocity of the gas is V infinity, and the area is A. Okay. The cross sectional area of the bed is A, delta P is the pressure drop across the bed. Okay. The net upward force, if you do a momentum balance on the bed of particles, is nothing but delta P times A. Okay. Now, this will be balanced by, this is acceleration to gravity, the weight of the bed, the volume of solid particles present in the bed, is okay, 1 minus epsilon times A times L. If AL is the total volume of the bed, only 1 minus epsilon fraction of this volume is occupied by particles, because epsilon is the porosity. So, only 1 minus epsilon of that fraction of volume is available for the particles to occupy. Okay. So, the net gravitational and buoyancy force on this solid particles is given by, I am going to multiply the solids volume by the solid density, the particle density, and then the acceleration due to gravity. Okay. When these are equal, when these two are equal, that is the onset of fluidization, because when initially when you, if you are to do a thought experiment, okay, I am going to plot delta p versus the superficial velocity. Okay. Initially, when you increase the superficial velocity, you will find that as per the packed bed relation, the delta p will be directly proportional to velocity if the Reynolds number is low. Okay. And after, at the onset of fluidization, okay, the delta p will remain constant, and then the, as you increase the superficial velocity, but what is happening instead is that the length of the bed, okay, which was initially constant, okay, that will start increasing. Okay. That is the onset of fluidization. Okay. So, essentially at the point when the delta p stops decreasing, starts to become a constant plateau, the length of the bed will start expanding. Okay. So, we are interested in finding what this onset point is, that is all we are interested in at this point of moment. Okay. So, essentially we relate delta p times A, the force, upward force is equal to the downward force at steady state at the onset of fluidization. Okay. And that is the, this will give you the criterion for minimum velocity for minimum fluidization, minimum velocity for fluidization. Okay. Now, so delta p, the two factors of A cancel out, delta p will be therefore G times 1 minus epsilon times rho p minus rho times L. Okay. So, let us, the porosity at the onset of fluidization will be the minimum compared to what when the bed is fluidized. The porosity at minimum fluidization velocity is denoted as, because when the length of the bed increases, the porosity will also increase, because the solids content is the same, we are not putting in any solids into the system, therefore, the porosity has to increase. So, let us call that EM. So, we are going to put EM here, that is a minimum porosity at fluidization, at the onset of fluidization. Okay. Now, at the onset of fluidization, delta p will be determined, because the bed just until the onset of fluidization, it is a fixed bed, it is a packed bed, it is not a fluidized bed. Okay. So, if it is a packed bed, we can use our earlier correlations to find what is the pressure drop. So, we are going to use the Ergon equation. Okay. So, we will find that 150 mu VOM is the minimum velocity for onset of fluidization, that is the notation in standard textbooks. Okay. EM squared by EM cube plus 1.75 rho v OM squared 1 minus epsilon m by phi s dp epsilon m cube is equal to G times 1 minus epsilon m times rho p minus rho, because I am writing an expression for delta p divided by L. So, therefore, you will have only the L factor will not be there anymore. Okay. So, I can rewrite this further after taking into account 1 minus epsilon m to the other side, I will get 150 mu VOM, the onset of fluidization, phi s squared dp squared times 1 minus epsilon m by epsilon m cube plus 1.75 rho V O m squared divided by phi s dp epsilon n cube g times rho p minus rho. So, this gives you a quadratic equation for V O m, because this is linear while this is quadratic in V O m. V O m is the unknown. So, we can solve it in principle provided we know all the other properties of the bed, okay, such as the porosity and so on. Now, for very small particles, for REP small compared to 1, only the laminar flow part will dominate, this part will dominate. So, V O m is approximately g times rho p minus rho times epsilon m cubed divided by 1 minus epsilon m divided by 150 mu times phi s squared dp squared. Okay. And when the Reynolds number based on the particle is large, 100 let us say, V O m, we neglect the first term and take only the second term. So, this will be the dominant term when the Reynolds number is large, okay. REP greater than 100, we will use the second term to balance the right side of the equation to get phi s dp g rho p minus rho epsilon m cubed divided by 1.75 rho, okay. This is to the power half, because that term has V O m squared. So, you will have to take this, if you neglect this term, okay, and take only this term, and you have V O m squared. So, you take the square root to get what is V O m. Okay. Now, so these are the onset velocities for fluidization at both low and high Reynolds numbers. So, we now know how to estimate what is the minimum fluidization velocity for a fluidized bed, and when the particle Reynolds number is small of the order of 1 and smaller, then we can use the relation wherein V O m is directly proportional to, well, we will just write down the expressions again. V O m for smaller Reynolds numbers, we need this expression for the following discussion also. It is approximately g times rho p minus rho divided by 150 mu times epsilon m cubed divided by 1 minus epsilon m times phi s squared dp squared, and there is a similar expression at higher Reynolds numbers. Now, another question that we can answer with our analysis so far is that suppose you have a fluidized bed, okay, a bed is fluidized and you are in this regime that the length of the bed is now expanding and you are at a particular, this is the length, this is the pressure drop, you are at particular pressure drop where pressure drop is constant, this is the superficial velocity and the length is at some expanded value. The question you want to ask is whether the fluidization velocity in this regime is such that it can, because during fluidization continuously gas is coming in and going out. While the gas is going out, we should take care, enough care that it does not entrain particles along with it, because the whole point of our fluidized bed is to keep the particles inside the bed in a animated sense of motion to enhance mixing and other transport properties, okay, and improve transport properties. So, how do we check whether the particles will entrain or not? Well, the answer is very simple. So, imagine that the fluid onset the velocity of the particles is slightly above the fluidization velocity. Now, so the velocity of the fluid, so there will be a force acting on the particles which will tend to, drag force acting on the particle which will tend to push the particle in that direction, while there will also be if you look at each particle. Now, let us not assume that the particles are in touch because they are already fluidized, so they are somewhat independent, although they will be colliding once in a while. So, we can roughly estimate whether the particle is going to stay inside the bed or it is going to go out by just comparing the fluidization velocity with the terminal velocity of the particle. Okay. So, what is the terminal velocity of a particle? Okay, that we know at low Reynolds number is g. So, we can divide the terminal velocity by the onset velocity for fluidization, g dp squared rho p minus rho by 18 mu. This we derived in the last lecture or the lecture before, and then we divide it with the fluidization velocity for low Reynolds numbers, and then you will get okay. Now this is nothing but is 8.33 1 minus epsilon m divided by phi s squared epsilon m cube. Okay. For spheres, phi s is 1, so spherical particles, okay, and if you use epsilon m is roughly 0.45, which is typical value. So ut by v o m, okay, becomes of the order 50. So the terminal velocity is 50 times the fluidization velocity. Therefore, it is very unlikely for the particles to be entrained by the flow, because there is a very strong component of the terminal velocity which will tend to bring the particle down. Again, it will collide with other particles, and then it will go somewhat up, and then it will be pushed also by the drag force of the fluid, but there is a very high chance that it will not go outside the bed, it will not be entrained. But let us look at the same case at higher Reynolds numbers. Okay, let us say REP greater than 1000. Then we will use the turbulent flow correlation for the onset of fluidization, velocity for onset of fluidization. Then you will get it is 1.75 times g times rho p minus rho by rho half. So ut by VOM is equal to 2.32 divided by epsilon m to the power 3 halves. So if you put epsilon m as 0.45, okay, you will get ut by VOM for the turbulent regime is just 7.7. Now this implies that there is a higher chance of particles being entrained when the flow is in the turbulent regime, when you compare it with the ratio where ut for laminar regime, where ut by VOM was about 50. So in the turbulent regime there is a chance that the velocity the particles will be entrained by the flow, because the ratio of the terminal velocity to onset of fluidization velocity is very it is not that high as in the case of laminar flow. Okay. Now this is all I want to talk about fluidization. The next application I am going to talk about is agitation and mixing of liquids. Okay. So in agitation and mixing of liquids is a very important unit operation in chemical industries, because we have many reactors and separators in which you have we have the necessity to mix two streams. For example, you could have a gas stream and a liquid stream, and you want to suppose you have a liquid and then you are bubbling gas, okay, and you want to be able to mix these two things well. Typically we use what is called an impeller, which is a rotating element to agitate the whole system, so that these two things are come into, these two phases are well mixed, okay, within the reactor or a separator. Okay. So purpose of the reasons why we agitate, okay, is to suspend solid particles on a large scale. You may want to blend immiscible fluids. And thirdly, we may want to disperse a gas through liquids, like I just discussed, dispersion of gas in a liquid, okay, and or dispersion of a second immiscible liquid in another liquid with the first in the form of drops. Okay. And of course, we want to enhance heat transfer. Let us say you want to remove heat effectively from the, suppose you have a container and you have a jacketed coolant or a heating fluid, then in order to remove heat very well, you have to mix this thing very well, heat transfer enhancement and so on. There are many reasons why agitation is used in chemical industry. Okay. And a typical agitator will look like this. You will have a typical agitated vessel will look like this. You have a jacketed vessel. So, let me draw the jacket wherein you use heating fluid or a coolant. Okay. And then you have an impeller, and the impeller is driven by a motor. Okay. And this is an impeller, and then you have on the sides you have baffles. Okay. To reduce tangential motion of the liquid. Okay. So, this is, and typically the liquid that is present will have a free surface. Okay. This is a free surface of the liquid. Okay. So, there are two types of impellers. One is axial flow impellers, and radial flow. The major difference is that the axial flow impeller, which looks like this, is like a propeller. Okay. This is the free surface of the liquid. It tends to push the fluid like this, and by continuity the fluid has to come like this back into the impeller. In contrast, radial flow impellers will look like this. This is the free surface. The fluid will go out like this and then come in like this. Okay. So, this pushes the liquid radially and tangentially. There is no vertical motion at the impeller. Okay. Here at the impeller there is vertical motion. Okay. And that is the key difference between these two impellers. Okay. Now, the flow patterns that happen in an impeller, they are very complex. Okay. And so, if you want to design an impeller, what we would like is from a fluid mechanical point of view, suppose you want to make the impeller rotate at a particular velocity, angular velocity. And the question we typically ask is what is the power requirement of the motor. Okay. That is from a purely fluid mechanical point of view. There are other important questions related to mixing and agitation. For example, how does the flow pattern change the efficiency of mixing and so on. Those are more microscopic aspects of fluid flow and transport phenomena, which we cannot deal in detail in this course, but here we will restrict ourselves to purely macroscopic fluid mechanical aspects, such as what is the power requirement of the impeller. Okay. Although the other questions are also very important, but those are beyond the domain of this course, beyond the confines of this course. So, essentially we use dimensional analysis whenever we have such a very complex problem in engineering applications. A useful tool in design is, as I have been mentioning several times in this course, is experimentation guided by dimensional analysis. So, what are the various variables present in the problem? One is the power, rate at which work is done by the impeller on the fluid, that is the power requirement of the pump. It must be a function of the angular velocity of the impeller, okay, that is denoted by small n in this notation. Okay. So, this is the revolutions per second. Okay. So, per time. Now, the diameter of the impeller, viscosity of the fluid, okay, gravity, density. Gravity is important because there is a free surface. So, the formation of vortices and so on will be affected by gravity. Okay. So, you have so many dimensional variables. We will use the pi theorem. I will not go into the details. Okay. So, if you do dimensional analysis by using the standard recipe that I have mentioned before in this class, we will get phi rho is a function of n dA squared rho by mu times n squared dA by g. Okay. This is the Reynolds number. This is called the power number. These are all non-dimensional groups. Power number. This is the Froude number. Okay. N times dA is the linear velocity of the tip of the impeller times dA rho by mu is the Reynolds number. The Reynolds number is a velocity scale times the length scale times density by mu. The velocity scale is given by n times dA in problems involving rotary motion of the impellers. So, this is essentially a Reynolds number, okay, n dA squared rho by mu. Power number is a non-dimensional power of the system, a requirement of the system. This is analogous to friction factor in a pipe. In a friction factor, we worry about the non-dimensional pressure drop. Here, we worry about the non-dimensional power requirement of the system. So, by doing dimensional analysis, we found this, but in reality, there could be other shape geometrical non-dimensional ratios. For example, what is the distance between, okay, this is not all, because you have to worry about all the other geometrical similarities. The distance is here, and the distance between the free surface and the impeller. All these non-dimensional ratios must be the same if you want to be able to scale up across sizes and across from lab scale to the prototype. So, there are other shape factors or geometrical factors which must be included in the correlation. So, we will just include them like this, comma S1, S2, S3. These are various shape factors which are essentially non-dimensional ratios of, let us say, this length S1 star divided by the diameter of impeller is S1 and so on. There are various other length ratios that must be equal in order for us to be able to ensure geometric similarity across scales. Okay. We cannot merely require, we cannot say that only if Reynolds and Froude number are same, you will have similarity, because there are other shape factors also which are important. Once we do that, now the power number is a function of the Reynolds number, Froude number and shape factors. Okay. Now, then you can use experiments to correlate the power versus speed data, and then you will get various curves. Okay. So, these are the curves that are obtained experimentally, okay, and for different impellers and so on for different. Okay. So, these are the curves that are obtained, and once these curves are obtained, one can use this information, okay, and once these curves are there in the form of handbook, one can use this information to scale up impellers and mixing and agitation vessels from lab scale to prototype insofar as the power requirement. Okay. Of course, as I mentioned, there are other issues involved in the design of agitators and mixers, because we have so far not worried about the actual purpose. The purpose is not to just design an impeller with power requirements. Our ultimate purpose is to worry about mixing efficiencies and so on, but those are beyond the scope of the present introductory course, and those will form parts of advanced courses in transport phenomena. Okay. So, right now all we can convey at this point of understanding is that in order to design mixing and agitation vessels, we have to use the concept of power number to scale up as a function of Reynolds number to scale up from lab scale to industrial or prototype scale in order to find what is the power requirement of mixing and agitation vessels. Now, in the remaining few classes lectures that are left with us, we are going to discuss in detail what are turbulent flows. Okay. We have discussed a few applications in chemical engineering process industries, namely flow through packed beds, flow through fluidized beds. Then we had discussed mixing and agitation, and we had discussed a little bit on flow of particles and settling velocities and settling chambers, and how they can be understood using fundamental principles of fluid mechanics with suitable approximations. And the next segment, last remaining 3 or 4 lectures, I want to focus on understanding turbulent flows in a little bit more detail than what we have seen. We have so far only described what is a turbulent flow. We will try to understand them in a little bit more detail, and we will stop here at this point in this lecture. We will continue in the next lecture on turbulent flows.